Hello and welcome to this Unisensor microsensor lecture. My name is Lars Hauer Larsen and I am CSO here at Unisense and responsible for production and development of Unisense microsensors. In this guide I will discuss which sensor tip size or sensor type to choose for different profiling applications. It often comes down to a choice between robustness and being able to measure the profiles correctly, and it is therefore of great importance to get the right sensor for a given application, as this might be defining for success or failure. Manuscripts based on data obtained by a too large sensor for a given application might very well be rejected by an author with domain knowledge. These are the topics I will cover in this guide. Why tip size matters, profiling and tip size, how to judge whether a tip size is appropriate, size and diffusion boundary layers, needle sensors for profiling, and at last I will briefly go through a selection guide in table form. In most biologically active matrices, transport of dissolved substances relies on molecular diffusion, and diffusion is, as you probably are aware of, at a scale of the bacterium extremely fast. On a larger scale, diffusion is extremely slow and it's a really slow transport process. In other words, on a scale of a 10 micrometer sensor, diffusion is fast, and on the scale of a 500 micrometer tip, diffusion is slow. This is very important to consider when choosing the right sensor, because the sensor tip blocks free molecular diffusion and have therefore the potential to disturb natural gradients, and this potential problem applies to all sensor types, including ampermetric, potentiometric and optical microsensors. The smaller the tip is, the less does it disturb the gradients. This slide shows the area of sensors with different tip diameters. As seen, the area of a 100 micrometer tip is 100 times larger than a 10 micrometer chip. In all measuring aspects, a small sensor is superior to larger sensors. The only downside is that it is fragile and breaks easily. So typically compromises must be considered, as not all biologically active matrices is microsensor friendly. For illustration of the problem associated with profiling with a large sensor in gradient systems, let us consider a gradient system with a large oxygen consumption rate. And we would like to measure the oxygen profile in this matrix. Oxygen is supplied from the overlying water only by molecular diffusion. We start with measuring the profile with a 10 micrometer oxygen sensor and get a nice parabolic shaped profile. We can do this over and over again in the same point without any change of the measured profile, indicating no disturbance. Now we substitute the OX10 sensor with a 500 micrometer OX500 sensor and we get a much steeper profile, and it is difficult to get replicates in the same spot. Why? Imagine a given cross-section within the sediment in the oxic layer. Because it is a 2D system, the oxygen concentration is the same over the whole area of this cross-section. When we look from below into this cross-section, we thus have an evenly distributed oxygen concentration, indicated with a uniform blue color, and the oxygen concentration in the section is in steady state, meaning that the oxygen consumption in the layer and supply rate does not change. Now we place a large oxygen sensor in the layer indicated with this circle. The oxygen sensitive area is in the middle of the tip. The glass tip blocks the diffusion to the bacteria under the tip, which cut off the supply of oxygen, which must diffuse around the sensor to get to the sensing point. But the bacteria consume a lot of this, and hypoxia start to develop under the tip. In contrast, a microsensor will not disturb the oxygen concentration due to the extremely efficient diffusion at small distances. Obviously, the problem gets bigger with a larger tip size and volumetric oxygen consumption rate. But how can you tell if the sensor is too big? Imagine again the matrix from before, and let us look closer into the data obtained when we profile. We will now take a look at the signal versus time and observe the signal change with each profiling steps for the small and the large sensor. The time between the increments are a few seconds longer than the response time of the sensor. We have oxygen concentration on the y-axis and time on the x-axis. We start the profiling and observe the online signal. The arrows indicate each depth increment. After some increments, we hit the matrix and the sensor signal starts to decrease with each increment until we reach 0 oxygen in a given depth. Looking closer on the signal change after an increment, it is obvious that we reach a stable plateau within the response time of the sensor. This proves that the tip does not affect the natural concentration. Let us now look at the same signal versus time pattern when profiling with the sensor with a large tip. The time between the increments are again chosen to be a few seconds longer than the response time of the sensor. What we see is that the signal does not reach a plateau within the chosen time between the increments. Looking closer into the signal change after an increment, we see that the signal still drops way longer than the response time of the sensor. Therefore, it is evident that the sensor disturbs the natural concentration by blocking the supply of oxygen to the sensitive area of the tip. You might think that this is only a problem which is associated with oxygen profiling, but this is a wrong interpretation. Let's consider a sediment where you have a zone where sulfide is oxidized with oxygen. Sulfide diffuses from deeper layers and is oxidized by sulfide oxidizing bacteria where the profiles overlap. If a large sulfide sensor blocks the oxygen supply, sulfide concentration will increase due to the lack of electron acceptor for the oxidizing process, and you will overestimate the sulfide concentration in this depth. Another issue when using large sensors is the disturbance of the diffusion boundary layer. The diffusion boundary layer is a thin layer of stagnant water, which thickness depends on the surface structure and the strength of the bulk water turbulence. The dominant transport process is diffusion in this layer, and it is therefore a barrier for exchange of solutes between the sediment and water. Turbulence will hit a sensor approaching the biologically active matrix for the purpose of profiling. The sensor tip will inevitably erode the diffusion boundary layer due to the guidance of turbulent water into the stagnant phase. The larger the sensor tip is, the larger will this disturbance be. So let us again look at oxygen profiles in a matrix with steep chemical gradients and a water phase above it. The oxygen concentration starts to decrease as the tip reaches the diffusion boundary layer. With a larger sensor, the bulk water oxygen concentration is pushed closer to the sediment surface, and thus the profile looks a little different. Therefore, estimations of matrix/water exchange rates based on measurements in the diffusion boundary layer can only be done with a very small tipped sensor, preferably max 25 micrometer. Needle-embedded sensors might seem like an attractive model for profiling due to the protection of the glass tip. However, this protection makes them unsuitable for profiling, especially in soft and organic matrices, due to the cavity between the sensor/electrode tip and the needle protection. This schematic illustration of a redox or ORP needle electrode tip is pointing out the problem. The cavity significantly limits the applicability for profiling in biologically active matrices, as the material will be pushed into the cavity and might be stuck there. This material will influence the redox potential measured in other layers, and the measurements might not reflect the real redox potential value. The material stuck in the needle tip might be very difficult to rinse away after use. For profiling in soft sediments and biofilms, we strongly recommend using non-needle protected sensors and electrodes. It applies to all types of needle sensors and electrodes. The needle protection does not make it impossible to break. If the needle is pushed into a matrix containing obstacles which are not easily moved, the needle will start to bend, and as the sensor is pushed downwards, the glass inside the needle might break. A 500 micrometer chipped naked glass sensor with a conical design is actually often less prone for breakages when profiling in matrices. I have here made a table over different matrix types and associated tip sizes to them, but it is definitely not a complete list of possible matrices. The sensor tip sizes recommended to use for the applications are chosen so they, to my best knowledge, will be able to resolve natural gradients without disturbing them. It is not a guarantee for risk-free profiling. Unisense has often trashed sensors with intact tips. Ask for such dummy sensor with different tip sizes, which can be used for testing. This will help to choose the best possible sensor type. pH electrodes are more fragile than other microsensors/electrodes, and they should therefore normally be used with larger tip sizes compared to other sensor types to get the same robustness for a given application. Oxygen optrodes have a limited use for profiling. The dye matrix is vulnerable to the grinding effect in inorganic matrices, and in soft matrices, for example biofilms, they do not offer as high spatial resolution as the amperemetric oxygen sensors. Thank you for watching this Unisense microsensor lecture. I hope you enjoyed it. If you have any questions, you are more than welcome to contact us at sales@unisense.com.